Okay, welcome to the last lecture on Fourier methods in combinatorial number theory. So this is being recorded, just so you know, and if you want to interact or ask a question, just be aware that that interaction will be recorded. If you do have a question, please do use the raise your hand feature or unmute to ask the question, or put the question in the chat. I'll try and monitor the chat as we go along, which has reminded me to get the chat pane up. Great, that's up. If anyone's got any accessibility issues with the video or the notes or the slides, let me know over email and we'll try and resolve those together. There'll be an opportunity to ask questions at the end when we're not live streaming or recording. So hopefully you won't feel so inhibited to ask questions then. We've had some great questions throughout the course, so please just unmute if you have a question. The notes are available on the course webpage or in the YouTube description. There's a link there to the notes. Okay, so provided everyone can hear me and see my slides, let's crack on. So today we're going to talk about the energy increment method, or an instantiation of the energy increment method, because we're going to use this method to prove the arithmetic regularity lemma, which we saw in lecture 3. And just to emphasize that the arithmetic regularity lemma, we gave one application, but it's a very robust tool, and one could foreseeably use it for lots of applications in combinatorial number theory. So it's worth knowing the statement and the lemma, and it's also worth knowing the proof, because for your specific application, you might need to tweak the proof to get the properties you want for your specific application. So I'm going to restate the regularity lemma. We're going to prove it by this technique of energy increment. And how we'll get this decomposition is by projecting our functions using conditional expectation onto what I call random Bohr translates. We'll go into that shortly. And finally, we'll conclude with the proof of the regularity lemma. So let me recap what the regularity lemma says. So the takeaway is you've got some one-bounded function. It doesn't have to be non-negative. It could be complex valued, but for the sake of convenience, let's specify to a one-bounded function, which is non-negative. And then there's a decomposition into a structured part, a small part, and a highly Fourier uniform part. So how should we think about each of these parts in our decomposition? So just to say, in lecture 3, we looked at decomposing the characteristic function of a dense set, but there's nothing really to be gained by specifying to functions of that form, and it's just as convenient to work with an arbitrary one-bounded function. Okay, so you should think about the structured part like a Bohr translate. The small part is some small exceptional set. So it's a function which, given any sort of statistic of your function f, the small part doesn't contribute significantly to that statistic. For instance, the L1 norm of your function, or a count of solutions to an equation weighted by your function. This small part won't contribute significantly to that count. And the uniform part is something which has no large Fourier coefficients. All of its Fourier coefficients are very small. Okay, and the application we gave was, we counted or gave a lower bound for the number of solutions to a translation invariant linear equation with variables restricted to some dense set A. Okay, and the point of the regularity lemma is it allows you to compute these global statistics, global counts, not local counts. You don't have to localize to a progression or a Bohr set in order to accomplish this. That's the power. So where are the quantifiers in this theorem? Well, first I'm going to get specific about what these heuristic descriptions mean. So what's a Bohr translate? So it's slightly unwieldy, but you should think about this as a smoothed out, low complexity Bohr structured function. So you might want to think about this function capital F as some sort of bump function on the torus, which is quantitatively continuous. It's M Lipschitz, where M is a sort of complexity parameter which measures the complexity of this bump function on an M-dimensional torus. So we've got two M's here, and both occurrences of M measure the complexity of our Bohr translate. So the smaller M is, the more simple the more translate. So we want to keep m small. Okay, so there's some frequency vector theta, has m coordinates, some smoothed, quantitatively continuous bump function on an m-dimensional torus f. Okay, what about the small function? So this is just a one-bounded function with small L2 norm. It's an epsilon proportion of its maximum possible size. And the uniform part is a function all of whose Fourier coefficients are very small. They're a 1 over f of m proportion of their maximum possible size. And this f is a arbitrary growth function. So the point of this uniform part, or what I'm saying here, is the error in the Fourier uniformity is arbitrarily smaller than the complexity of the structured part. So Fourier part is arbitrarily small in terms of the complexity of the structured part. That's what this growth function f is indicating. And here's a reminder of what m Lipschitz means, or approximately means. Okay, we've still got some quantifiers to add. So here are our quantifiers for any epsilon greater than 0. So we're specifying the smallness of our small part. We're free to do that. And we're specifying how fast our growth function grows. We're free to do that. So maybe you want this uniformity in your Fourier transform to be double exponential in the complexity of your structured part. Maybe you want it to be Tao-type decay. You can do that. So once you've specified your small part and your dependence in your growth function, you get a complexity parameter after specifying epsilon and f. Okay, so that's the way the quantitative dependence works. So this is just all a recap from lecture 3. So how are we going to prove this arithmetic regularity lemma? We're going to do it via some formalism of conditional expectation. We're going to chop up our interval into parts, b1 up to bs, and we're going to average our function on each part. So the value of our projection on our local average is determined by which part you lie in. So if you lie in this part, then we're going to average along this path. Let me get into the specifics of what that means. So first I want to set up this idea of partitioning our interval into disjoint sets, b1 up to bs. And I'm going to abuse notation and write B capital N to denote that part in the partition which contains the integer n. Okay, so for every integer n in this interval, there's exactly one and only one part, bi, containing that. And so we denote that b of n. So what's our conditional expectation? So I'm going to write the projection of our function f with respect to a partition b. So I've labeled this partition as b. It's just its value at n is the average of our function at the part corresponding to n, the part which contains n. Okay, nothing too much going on there. We're just locally averaging in the set to which you belong. So our strategy for the arithmetic regularity lemma is we're going to chop up the interval into a coarse partition. These are the bi's. And then we'll further chop it up into a refined partition. These are going to be bij primes. Okay. So we decompose each atom in our original partition into further subatoms. And we're going to define our structured part to be a coarse projection. We project our function with respect to this coarse partition. The small part is going to be the difference between a refined projection, a refined partition, the projection onto a refined partition, and the projection onto the coarse partition. And the uniform part is going to be the function minus its refined projection. So why is this a good idea? So if you're projecting onto a very coarse partition, you expect to have a very low complexity function. For instance, if your partition was just the trivial partition corresponding to the full interval, you just have the average of your function. And that's a very structured function. Okay. So you'd expect a coarse projection to have a lot of structure, provided you're projecting onto quite structured sets. So these atoms have to be structured, algebraically structured or Bohr structured or something like that. Now, a refined projection should pick up most of the behavior of your function f. For instance, if you project onto singleton sets, then you get back your original function. So a very, very refined projection essentially picks up all the behavior of your function. So you'd expect the difference between the Fourier transform of your function and the Fourier transform of its refined projection to be small in whatever norm you want. For instance, in the L infinity Fourier norm. Okay. So provided your partition is structured, the coarse projection should be structured. And provided you've got a very refined partition, you should have low error in your Fourier uniformity. And the art in the arithmetic regularity lemma, or in any regularity lemma, is finding two partitions such that the difference between their projections isn't too large. So it's not clear at first sight that you can find a coarse partition and a refined partition such that the difference between their projections in L2 norm is small. And that's what we're going to have to work hard to prove, that there is such a coarse and a refined partition. Okay. So that's sort of the overview of where we're going. But what is our partition? What partitions are we going to use? What structured sets are we going to chop our interval into and then project down onto these structured parts? So we're going to embed our interval in the unit circle via one of these homomorphisms. So you fix your frequency theta, and you take an integer in your interval, and you homomorphically embed it in the unit circle via the homomorphism determined by the frequency theta. Okay. Now we want to partition our interval, so we'll partition our circle and then pull each part of that partition back to the integers. How are we going to partition our circle? We're just going to chop it in half. Okay. So we'll chop it at an angle of 2 pi I alpha. And that gives us 2 halves of the circle. And we can pull each half of the circle back. This part corresponds to our first half. You start at an angle of 2 pi alpha, and you go all the way to 2 pi alpha plus pi. And this corresponds to our second half. So we can definitely do this. This is definitely a partition into 2 sets of our interval. So more generally, we're going to partition in what I'm going to call Bohr translates. So you fix a vector of frequencies, theta. So theta is some choice of frequencies, theta 1 up to theta d. That gives you d homomorphisms, okay? And you also fix a choice of angles, alpha 1 up to alpha d. These correspond to the choice of slices of our circle. So we've got d copies of the unit circle. We'll slice it into d different ways. And then the partition, we can either shift this interval by nothing or by a half. Okay, so shifting by nothing corresponds to this half of the circle, this arc. Shifting by a half corresponds to this arc. That's encapsulated here. Now, if we've got d copies of the circle, for each copy of the circle, we can either choose to shift by 0 or a half. So we've got this half times epsilon, where epsilon is a choice of, it's a 0, 1 d-dimensional vector. Okay. So this collection of sets definitely partitions our interval into 2D sets, 2D Bohr translates, 2 to the d. Okay, so this isn't going to be my notation. It's hard to parse on first sight. Essentially, you don't need to worry too much about the definition, just to know that we've got some partition 2D parts corresponding to different choices of epsilon, and they have the structure of Bohr translates. Okay, so just to emphasize that each set of this form, the theta, alpha, epsilon, it's like the intersection of d copies of sets of this form or this form. So you choose which of these two parts in your first slice you're doing, and you do that for d copies of the unit circle. Okay, so these are the structured sets we're going to project down onto. Bohr translates. But we're going to project randomly, okay, because we want our projection to have like lots of nice Lipschitz properties. We want it to be very continuous. And the best way to do that is to choose this alpha, the shift parameter, randomly from the unit circle. So we're going to slice our circle d times at d different random angles. Okay. So again, abusing notation, you can write b theta alpha of n to be the part in the partition containing n. And here's our shorthand for our conditional expectation operator. F theta of alpha is the, evaluated at n, is the average of f on the part of the partition corresponding to n when we fix our d homomorphisms corresponding to the frequencies theta 1 up to theta d, and our d shifts, our d cuts of the unit circle corresponding to our choice of angles alpha 1 up to alpha d. Okay, so this isn't quite good enough for the continuity properties we want. And to get the continuity properties we want, we're just going to average over all possible choice of cuts of our circle. So we choose alpha uniformly at random from the d-dimensional unit, from the d-dimensional torus. So this is going to be our projection. And it's only determined by one vector, theta 1 up to theta d, a choice of frequencies, d frequencies. So here's the picture in your head again. You randomly slice the circle, and you average your function on either half, on either side of the line, on the arc occurring on either side of the line. Okay, let me show that these random translates control our L infinity Fourier norm. So for any function f on this interval, you can find a frequency theta such that the L infinity Fourier norm is bounded in terms of the correlation of our function f with one of these random translates, these random Bohr translates. So it's a little hard to parse this when you first see it, but I'm just saying that if f has a large Fourier coefficient, then it correlates with one of these Bohr translates with alpha chosen uniformly at random from our circle. So how does the proof go? It's just calculus, so there's nothing much going on. You can write a phase, En of theta, in terms of an integral. So the phase En of theta is equal to the integral of this Bohr translate as alpha ranges over the circle, twisted by some phase, E of alpha. That's just calculus. So let's substitute this integral into our definition of the Fourier transform. The Fourier transform at theta is this sum in absolute value. You can replace each linear phase here by this integral, and that's what we get here. Now, integration is linear, so we can take it outside of the summation. And this twist, this phase that we're twisting by when we integrate, it's independent of our summation. So we can also take that outside the summation and then crash through with absolute values to destroy the phase and just get absolute values here. And that's the expression up here. Okay, so there's not too much going on here. We've just done a little bit of calculus. But what this is saying is that correlating with these random Bohr translates measures the same thing as the Fourier transform. So now I want to talk about this energy increment procedure. How does that go? So let me remind you about how we project our function down onto these Bohr translates, determined by theta and alpha. Theta is the frequencies, alpha is the shifts, or alpha corresponds to the cut of our unit circle. And then we average in alpha. So this gives us our projection f theta of n. That's just a reminder. Now we want this projection to resemble our original function f, Fourier-analytically. We want them to be indistinguishable from a Fourier perspective. So we want the difference between their Fourier transforms to be small, an epsilon proportion of the maximum possible size. We don't know if that's true or not. If it's not true, can we say something? Okay, so suppose we don't have a good Fourier approximation. What can we deduce? Well, just rewriting out definitions using our random translate inverse theorem, we know that this difference, f minus f theta, it correlates with some random Bohr translate. Okay, that's just the random translate inverse theorem we proved on the previous slide. Now this f theta encodes an additional integration here. So let's expand in terms of that integration and then take the integration to the outside of our absolute values. Okay, so now we're integrating over a d plus 1 dimensional torus. And we've got two alpha parameters. We've got the vector, the d-dimensional vector alpha, and the one-dimensional vector alpha prime. And this projection is determined in terms of the d-dimensional shifts alpha, and this random translate is determined by the one-dimensional translate alpha prime. I just want to rewrite that in terms of an inner product. So if you normalize inner products appropriately, you can rewrite that summation as an inner product between our difference f minus f theta alpha and this random Bohr translate. Now, the trick here is that with respect to the partition given by b theta, theta prime, alpha, alpha prime, epsilon. Okay, so I'm partitioning according to d plus 1 frequencies and d plus 1 cuts. And there are 2 to the d plus 1 choices of epsilon. That is a definite partition. And both this function and this function are constant on these atoms of that partition. So it's just an exercise in inner products and conditional expectation to know that if you've got two functions here and here, which are constant on these atoms, then you can replace this function by its average on these atoms at no cost. Okay, so this is an identity, and as it's an algebraic identity, it's very easy to check. I'm not going to do that checking for you. You can just take it on trust. But what have we got? We've got, because these are constant on these atoms, we can replace f by its average on the atoms. Okay. Now we're going to crash through with absolute values and the Cauchy-Schwarz inequality to forget about this function here. And we've just got the squared L2 norm of the difference between a coarse projection and a projection of one dimension higher, one dimension more refined. That's here. And it's this quantity we're going to call the energy of our partition, or this is the difference in energies of the partitions. Okay. So again, another exercise in conditional expectation and inner products. Not too hard, it's just algebra, or easy algebra, right? The kind of algebra I do, not hard algebra. You can check that this coarse projection is orthogonal to the difference between the coarse projection and the refined projection. So by Pythagoras' theorem, the L2 norm, or the energy of our refined projection, is equal to the energy of the coarse projection plus the energy of the difference between the projections. Okay. Now we know this thing is large from this string of inequalities. So what we've shown is if we don't have a nice Fourier approximation, the Fourier approximation we're looking for, the energy of the new projection is bigger by an epsilon proportion than the energy of the old projection. So we've incremented the energy. So Fourier non-uniformity implies energy increment. So you can enact this energy increment and prove the following. You've got some one-bounded function and you've got some epsilon parameter, which is going to measure the error in your Fourier approximation. Once those have been fixed, you can find a dimension of a torus, D, bounded in terms of epsilon, and a frequency vector, theta, such that the random Bohr translate projection of F with respect to this frequency vector, theta, is close to F in the L infinity Fourier norm by an epsilon proportion. So we call this a weak regularity lemma. And the reason it's weak is the complexity of our approximation, which is measured by D, and the error term in the difference of Fourier transforms, they're related, but they're not related in a with arbitrarily good dependence. So in our full regularity lemma, we're going to be able to get a Fourier approximation which is arbitrarily small in terms of the complexity of our approximation. But we don't have that here. Nevertheless, this weak regularity lemma is very useful, and you can use it to improve Roth's bound on the density of sets lacking three-term progressions. If you do some higher order Fourier analysis, this technique can bound the density of sets lacking four-term progressions. You can attack the nonlinear Roth configuration in the integers with these ideas. So it's actually quantitatively very useful, this weak regularity lemma, but it's only useful in a context when you're prepared to localize, okay? And the full regularity lemma is about global statistics, and the weak regularity lemma is not very useful for global statistics. It's good for local statistics, when you're happy to count in a subprogression or a Bohr set. So that's weak regularity. And what we're going to do with this weak regularity lemma, again, this is just proved by incrementing energies like we saw on the last slide. What we're going to do is we're going to iterate the weak regularity lemma to prove a stronger regularity lemma, which is our full arithmetic regularity lemma. Now, in order to do that, we need to prove a more general version of the weak regularity lemma, which looks a bit technical on first sight. So I want to prove a similar weak regularity lemma, but this time I want my approximant, my projection, to be a refinement of a projection I've already sort of been given. So imagine you've been given a projection with respect to this vector theta 0 of dimension d0. So this more refined version of the weak regularity lemma says you can refine your vector theta 0 by adding a bunch of new frequencies whose dimension is determined by the level of approximation you're after. You can refine your frequency vector and get a better Fourier approximation. Okay, so this is going to be useful when we prove the full regularity lemma, because we're going to be trialing various frequency vectors theta, and every time, if we don't get the Fourier approximation we're after, we're going to refine again and extend our frequency vector. Okay, and the fact that this is valid is given by this more technical version of the weak regularity lemma. But don't let that worry you too much. It's proved by exactly the same argument, the same energy increment argument we just gave. So let's get on to the full regularity lemma now. How do we prove that? So what we're going to do is we're going to trial a bunch of projections until we get a projection that works. Okay, so maybe our first trial would be to take our approximant just to be the simplest possible projection of averaging our function and multiplying it by the indicator function of the interval. That's got dimension 0 as the partition, the random Bohr partition underlying that projection has dimension 0. And we want the quality of our Fourier approximation to be f of the complexity of our structured projection. This structured projection has complexity 0. So applying the weak regularity lemma, we can refine our first attempt at a projection to a new projection, f theta 1. And we can guarantee that this new projection has a Fourier error, which is arbitrarily small in terms of the complexity of our first attempt. But what we really want is we want this Fourier error to be arbitrarily small in terms of the complexity of our actual new projection, and it might not be. Okay. Nevertheless, let's persevere. So now we've got a new projection of a complexity d1, and we want a Fourier error which is arbitrarily small in terms of d1. So we hit this with the weak regularity lemma once more. We obtain a new dimension, a new set of frequencies, and a new projection, a refinement of our previous projection. And this time the Fourier approximation is arbitrarily small in terms of the complexity of our previous approximation. So our new approximation has complexity d1 plus d2. That's the length of this frequency vector. So again, we apply the weak regularity lemma to get a Fourier approximation which is arbitrarily small in terms of that complexity d1 plus d2. And the price we had to pay for that is adding a new frequency vector theta 3 to our projection. And we just carry on doing this. But let's recall our use of Pythagoras' theorem from the proof of the weak regularity lemma. This energy is non-decreasing as the partition gets more and more refined. So you refine the partition and you don't decrease the energy. Okay. So as we refine and refine this partition, we've got a non-decreasing sequence of real numbers. And because this function here is a bounded function, it's one bounded, this energy is bounded above in magnitude by n with our normalization. Okay, so we've got a non-decreasing sequence of real numbers bounded above by n. So at some point, two elements of this non-decreasing sequence have to be very close together. So by the pigeonhole principle, at some stage, j, we get two projections whose energy, the difference between their energies, is some epsilon proportion of n. Okay? That's just a basic fact in real analysis to do with increasing sequences. And by Pythagoras' theorem, this the energy of the difference of two projections is equal to the difference of their energies. Okay. So this has given us the regularity lemma, because this is going to be our small part now. Because you can take this integral into the inside of this L2 norm, and you've got the difference of two random Bohr projections. So let's recap. Full regularity says you specify your smallness, you specify your growth function. For any one bounded function, you can find a frequency vector whose dimension is bounded in terms of the growth and the smallness, and a second frequency vector. So this is what the regularity lemma says, it's what we've just proved. So what have we proved? We've proved that when we were iterating, finding longer and longer frequency vectors, we got to a stage where, well, at every stage of our iteration, the Fourier error between f and this refined projection was f of d, where d was the complexity of our previous iteration. And by the pigeonhole principle, we got that the L2 norm of the difference between the refined projection and the coarse projection was at most epsilon. So this is what we proved. Let's see why this gives us the arithmetic regularity lemma, because we're just going to set our structured part to be our coarse projection, small part to be the difference between the refined and the coarse projection, and the uniform part to be the difference between f and the refined projection. So the only thing we haven't verified is that the structured part looks like some smoothed out bump function on the torus. So let's verify that. So let's show that the structured part is M Lipschitz. So I claim if you give me any frequency vector of dimension d, then I can find a one-bounded function on a d-dimensional torus with Lipschitz constant at most 4d, such that the projection, the random Bohr projection with respect to this frequency vector, takes the form capital F of theta times n, exactly what we want. So how does this go? So first I want to define some numbers. So given a choice of cuts, alpha 1 up to alpha d, I'm going to define this number, f sub epsilon of alpha, as the average of our function f, and with respect to the frequency vector theta given by the lemma, and alpha is our choice of cuts, and epsilon is the choice of 0, 1 vector, corresponding to the part of the partition we're working. Now you can verify, let's not go into it, take it on trust, that our projection, our random Bohr projection, or random translate projection, looks like these numbers convolved with a bunch of boxes evaluated at the frequency vector times n. So what do I mean by convolution? On the convolution on the torus, I mean you integrate over all solutions to the equation gamma plus alpha is equal to beta for a fixed beta. Okay. So this looks a little hard to pass, but just take it on trust that you can write this projection as a convolution with respect to these numbers. Okay, so the obvious candidate for our function, such that little f theta of n is equal to f of theta n, when you stare at this formula, it's obvious that we should take these functions f to be the same function, just with theta of n replaced by an arbitrary element of the d-dimensional torus. So that's what we do, we set f to be this. Okay, there's an issue that some of these atoms might be empty. Let's not worry about that. Okay. So what I'm going to do is, if I want to show that this function has Lipschitz constant at most 4d, by the triangle inequality, it suffices to verify that each of these individual summands, so these individual summands, have Lipschitz constant at most 2 to the minus d times 4 times d. Okay? So if that's true, then by the triangle inequality, when I sum over all these choices of epsilon, I get a function with Lipschitz constant almost 4d. So I'm just going to verify this for the choice of epsilon equal to all zeros. So we're interested in how this convolution behaves when we perturb it by gamma. We're going to compare that to the convolution evaluated at the original point beta. So you substitute in the definition of convolution, and the f0 function is just a one-bounded complex number. It varies with alpha, but it's one-bounded. So we're going to crash through with absolute values in order to sort of get rid of these f0 functions. And we're left with a difference of two indicator functions of boxes. Okay. Now, we can change variables and introduce a new parameter which is equal to beta minus alpha. So maybe let alpha prime equal beta minus alpha. You make that change of variables. Remember, beta is fixed and alpha is ranging over the torus. And you can simplify this difference of indicator functions of boxes. So we've got the indicator function of the box shifted by gamma minus the indicator function of the box. And we're integrating. So we've just got the measure of the symmetric difference of these two boxes with one of them shifted. You can do a little bit of geometry to estimate this symmetric difference. And the bound I got was 2 to the minus d times 4 times the sum over all sort of fractional parts of this alpha vector. Okay. So that gives us the Lipschitz constant of 2 to the minus d times 4. And the d comes from this summation because we're taking the maximum, the norm we're working with, the metric we're working with on the torus is the maximum of these quantities. Okay, so that does give us this Lipschitz constant. Great, so that's all I wanted to say. I'm sorry if that lecture was a little bit technical. It's technical, what can you do? But it's a really important, if you work in combinatorial number theory, I think it's a very important proof to know because often tweaking this proof can help you use the regularity to answer the question you want to answer. Okay, so that's all I've got to say for this course. Thank you very much for your attention and for listening to these 6 lectures. It'd be fantastic if anyone wants to give me feedback. I've created a little Google Doc using a template, and I'd find that feedback really useful to let me know what worked and what could be improved for other iterations of this kind of course. Yeah, but thanks for your attention. So what I'm going to do now is I'm going to end the stream and stop recording.